Hello, everybody. Hello, everybody. And those of you, really nice to see you.
Hello.
Look. Can you hear me all right? Closer to the microphone.
We can hear
all right.
you.
Okay, so welcome. Welcome to the Aspen Center for Physics Colloquium. So my name is Tao Han from the University of Pittsburgh. I'm in the program for the new intersections, neutrino physics at the crossroad. So we're having a lot of fun. And today we are very happy and very lucky to have one of our participants, Professor Mu-Chun Chen, to deliver the colloquium. Okay. So Mu-Chun got her bachelor degree from the National Taiwan University, and she came to the US and completed her PhD degree at the University of Colorado Boulder. Welcome to back home to the state, home state. And Mu-Chun did her postdocs at Brookhaven National Lab and the Fermi Lab, and continued on to make an impact on our field, many important contributions. And she worked on the mass generations, in particular fermion mass and mixing, and most notably, construction of theoretical models for CP violation. And in particular, she is one of the leading experts on the neutrino mass theory and phenomenology. And she joined the UC Irvine as a faculty in the year of 2006. So she has been working on a very broad spectrum and a lot of important contributions to the field. And we're very, very lucky to have her in our program. And today she's going to tell us something about neutrino physics. The title of the talk is NoTORIous neutrinos. Okay, Mu-Chun, so take it over from here.
All right, so can you hear me all right? Okay, so thank you so much to Tao for this very kind introduction. Before I start, I would also like to thank the organizers for the neutrino workshop for putting together such a wonderful program, as well as all the Aspen Center for Physics staff for all their indispensable support. My very first Aspen workshop, it was actually on the topics of neutrinos back in 2004. And that was actually my very first time meeting several of the colleagues sitting in the audience. So it's really a great pleasure for me to be back here and give a colloquium on these particular topics. So since early 2000, there have been a lot of advancements in the field of neutrino physics. And today I'm just going to concentrate on one particular aspect, which has to do with the flavor donuts, as depicted by this nice drawing done for me by my 7-year-old very talented niece. So what can we do with a flavored donuts? A very obvious, this is a very obvious answer. Just let me try to fix this first. My apology. Yes, is to eat it, right? But as physicists, there are actually a lot more things we can do with the donuts, which also known as the tori, right? So as shown in this very nice drawing by our graduate student collaborator, Shreya Shukla, the shape of a donut is defined by this basis vectors on the lattice, or equivalently, this complex parameter, the so-called modulus parameter tau. And the choice of this vector, lattice vectors, is actually not unique. And equivalent tori are related by the so-called modular symmetries, as I will describe in more details in later part of my talk. Modular symmetries actually have a lot of relevance in both subfields in mathematics and in physics. Modular symmetries, this is a very relevant topic in number theory. The symmetries also abound in string theories, and they also found their applications in condensed matter physics, as some of the audience in the condensed workshop may know. But more recently, the modular symmetries have generated a lot of excitement in neutrino physics. And this all started in 2017, and I apologize, that thing actually is blocking the view. In 2017, in these questions originally posed by Ferruccio, namely, are neutrino masses modular forms, right? So that's what I will be concentrating on. All right. So as we heard a month ago by this wonderful public lecture by Professor Peter Onisi, which tells us neutrino is an elementary fermion that was invented by Pauli some 9 decades ago in order to save energy momentum conservation in nuclear beta decay. So before the invention of neutrinos, it was thought the beta decay was thought to be a two-body decay, where the electron share the energy with the daughter nuclei in the final state. Based on the energy momentum conservation, it was then predicted that the energy of the electron should peak at a single value, which contradicted with the observed continuous energy spectrum experimentally. So what Pauli proposed in order to come into the rescue is that instead of a two-body decay, actually the nuclei underwent a three-body decay with this third particle being the anti-neutrino in the final state. Right? So in this case, the energy momentum conservation actually predicts a continuous energy spectrum for the neutrino, for the electron. And so this, of course, agree with the observed energy spectrum, at the same time, maintaining the energy momentum conservation. There are 3 types of neutrinos, or like particle physicists like to call them 3 flavors. And these 3 flavors are defined through the weak interaction. So for the electron neutrino, and so of course, weak interaction is one of the 4 fundamental interactions of nature mediated by the W boson, as we heard earlier. The electron neutrino is a type of neutrino that participated in the weak interactions together with the electron, where the muon neutrino and tau neutrinos, likewise, are the type of neutrinos in the weak interactions in association with the muon and tau. Right. Let me just try to hope this is better after everybody already arrived in the Zoom meeting. All right, very good. So standard model is a gauge theory that describes 3 of the 4 fundamental interactions. One of the beauties of a gauge theory is the fact that once we specify all the gauge symmetries, and once we specify the complete particle contents, then all the interactions are uniquely determined, right? So this is actually robust. The particle contents of the standard model contains 6 quarks and 6 leptons, and there's 6 quarks and 6 leptons are organized into 3 generations, all right? The generation increases in mass, and the higher generation particles tend to decay into lower generation of particles. And therefore, in our everyday life, all we observe are just the first generation particles. All the fermions in the standard model come in both the left-handed and right-handed partners, except for the neutrinos. So here you already see the very first hint that neutrinos are somewhat spatial. Come on. Right. If elementary fermions in the standard model acquire their masses through the so-called Higgs mechanism, through the so-called Yukawa interactions upon the spontaneous breaking of the electroweak symmetry by the Higgs mechanism. So in the Yukawa interactions, basically the left-handed fermion and right-handed fermions, they mix and together interact with the vacuum exploitation value of the Higgs boson. And through this interaction, they acquire their mass. However, I just told you, in the standard model, there are no right-handed neutrinos. And therefore, the left-handed neutrinos cannot participate in the Yukawa interactions, and therefore neutrinos are predicted to be massless in the standard model. All right, so what I show you here is a spectrum of the masses in the standard model. And what you see immediately is a large disparity among them that come across some 6 orders of magnitude, ranging from the top quark mass of around 172 GeV, all the way down to the electron mass, which is about 0.5 MeV. And just to give you a reference, here I put in the neutron mass, which is about 1 GeV. So even though the Higgs mechanism gives rise to masses to the elementary fermions, the Higgs mechanism itself doesn't really explain this observed mass pattern. Right? So there's some deficiency of the standard model. In fact, in the standard model, all these masses are given by a set of undetermined Yukawa interaction. Basically, these couplings characterize the strength of the Yukawa interactions. Right? So the larger the coupling constant is, the heavier the particle mass is. Furthermore, standard model predicts massless neutrinos. So in addition to this mystery regarding this huge disparate mass patterns, another mystery in the standard model is the fact that the states of the quarks that have definite masses are different from those states that participate in the weak interaction. And this mismatch actually occurs across all 3 generations. It is described by the famous CKM mixing matrix, which is a unitary 3x3 matrix that contains 3 mixing angles and 1 phase. And due to this mismatch, this is what generates. This is basically responsible for all the processes in the standard model where quarks transmute from one family into another. All right. So among those processes, one example is oscillation of the neutral kaons into its own antiparticle through their free flight in space through the interaction with the W gauge bosons. So how about the neutrinos? As we see, standard model predicts 0 neutrino masses. So what that means is all the 3 masses are degenerate. And from your linear algebra, what you learn is that in this case, I can choose my mass eigenstates to coincide with the weak interaction eigenstate. And what this is telling us is that there appear to have accidental, enhanced accidental symmetries, which give rise to selection rules that forbids processes that come across the family lines in the lepton sector. Right? So as a result, in the standard model, there is no neutrino oscillation. Furthermore, various charged lepton flavor violation decays, such as muon decays into electron plus a photon, is forbidden. And there, of course, a very active experimental program worldwide right now underway, trying to look for these rare processes and thus testing the selection rules. Right. So over this, 9 decades after its invention by Pauli, there have been, of course, a lot of major discoveries in neutrino physics. And all of these major discoveries have led to 4 Nobel Prizes. These discoveries include the detection of muon neutrino by Lederman, Schwartz, and Steinberger in 1962. The detection of electron antineutrino by my late UCI colleague Fred Reines in 1958. The detection of solar neutrino and supernova neutrino by Davis and Koshiba in 1968 and 1987 respectively. And most recently, the detection of neutrino oscillation by Super Kamiokande collaboration led by Kajida-san and by Snow collaboration by Professor Art McDonough in 1998 and 2002 respectively. So in this most recent discovery, of course, we learned this opens up actually a brand new era in particle physics because the discovery of neutrino oscillations indicate that neutrinos have masses. And therefore, this provides the very first, very compelling, solid evidence of physics beyond the standard model. Right, so the field afterwards actually evolved very rapidly in the last 20 years. We have come a very long way in measuring various oscillation parameters. So for many of these parameters, we already enter from the discovery phase into the precision phase. However, as I will show you in a few slides, there are still many fundamental properties of the neutrino that we do not know, and therefore we are still awaiting for many great discoveries to come. So now that neutrinos have masses, just like in the quark sector, there could be a mismatch between their mass eigenstates and weak interaction eigenstates. And that mismatch is described by the so-called PMNS matrix, right? And it is due to this mismatch that neutrino oscillation is possible. And neutrino oscillation, of course, is a very good example of quantum mechanics at the macroscopic scale. So at the production points, the neutrinos of a definite flavor are being produced by the weak interaction, right? So depending on what source of neutrinos you have, whether it's accelerator or the sun or whatnot, you produce neutrinos of a definite flavor. Through their propagation between the source and the detector, neutrinos evolve according to their masses, a la the Schrodinger's equation. Once the neutrinos reach the detectors, again, neutrinos of a given flavor are being detected via the weak interaction, right? So depending on the distance between the detector and the neutrino source, there could be a different flavor composition being detected at the detector from the flavor composition, meaning 100% of neutrinos of a given flavor type. So this is the basic of neutrino oscillation. So where do we sit? The current experimental data are nicely summarized in the following two pictures. So I should probably rephrase it. Both pictures that I show here are consistent with the current experimental knowledge. On the left, this is a so-called normal ordering. And what it means is this nu3 mass eigenstate is the heaviest mass eigenstate, followed by nu2 and nu1, right? Where on the right, this is again still consistent with experiment. This is called the inverted ordering, where the nu3 mass eigenstate is the lightest state, where nu2 and nu1 are the heavier states. And what I meant here by the mass eigenstates, these are defined through their flavor compositions, as I indicated by the composition of these color bars, which indicate the part of nu e, nu mu, and nu tau with respect to these different colors. Oh yes. So this bigger the difference between the mass square between nu3 and nu2, this bigger delta m squared difference, this is what drives the atmospheric neutrino oscillation, where this smaller delta m squared is what drives the solar neutrino oscillation. And experimentally, we know the delta m squared atmospheric is on the order of 10 to the minus 3 electron volt square, where this solar delta m square is on the order roughly of 10 to the minus 4 electron volt square. where for the 3 mixing angles, what we know now is that 2 of them are rather large, where the smallest one, meaning theta 1, 3, it actually has a value which is compatible with the capable angle, which is the largest mixing angle in the quark sector. Right. All right. So even though we've learned a great deal about the mixing parameters, there are still many fundamental questions regarding to the neutrino properties that we do not know. And personally, I think the most fundamental question among them is the Majorana versus Dirac nature of the neutrino, namely whether neutrinos are their own antiparticles. Okay. Another fundamental question is whether or not there is charge parity violation in the neutrino sector or lepton sector. Of course, this question would have very important implication to the origin of the cosmological matter-antimatter asymmetry. Given that the oscillation experiments only tell us the delta m square, meaning the mass square differences, we don't have any clue about the absolute mass scale of the neutrinos. And again, knowing the absolute mass scale of the neutrino is important because this is closely tied to the scale of the new physics for neutrino mass generation. Okay. And a related question, of course, is the mass ordering, whether it's inverted versus normal that the nature chooses. And another interesting question is whether there's additional neutrino species, namely the stereo-neutrinos. And the last but not least, that concerns the precision. And in particular, this is a precision on the theta 2, 3. The current measurement is rather close to maximal. But whether it's exactly maximal or it deviates from maximal, this could have implication to the underlying physics or symmetry that are to explain the pattern of masses and mixing angles. All right, and of course, there's a suite of current and upcoming experiments trying to address some of these puzzles. All right, so those are sort of like fundamental properties about neutrinos. But theoretically, the current data also pose great challenges. In particular, there are 2 challenges that I would like to address in the later part of my talk. One has to do with the fact that if I put in now the compatible neutrino mass pattern in this full mass spectrum, what you discover is that now this disparity come across 12 orders of magnitudes, right? So this is much larger. So the question is, why are neutrino masses so much smaller compared to the charged fermion masses, right? And another aspect that in regards to the flavor structure. Experimentally, we know the CKM matrix, the CKM mixings are rather small. So what that means is the CKM matrix would assume this form, which is closely to identity, right? So quarks, they do not mix so much. However, in the neutrino sector, the mixing are very large, right? I just show you the smallest mixing in the neutrino sector actually is compatible to the capable angle, the largest mixing in the quark sector. So neutrinos, they mix a lot. So the question is, how do we reconcile these 2 drastically different mixing patterns in a consistent theory, right? All right, so again, the patterns of fermion masses and mixing, this is not really addressed in the standard model. Instead, they resort to a large number of free, undetermined, unrelated, independent parameters in the standard model of the Yukawa sector. And to be more precise, in the standard model, we have in total 28 free parameters, depends on how you count, so there's some subtlety there. But in total, I have 28 free parameters. Out of the 28, 22 are in the Yukawa sector, right? So this is actually a big part of the parameter in the standard model. So the goal here is to ask, where do fermion mass hierarchy, flavor mixing, and CP violation come from? Whether there's more simpler organization principle, so that we maybe even further reduce those 22 or 28 parameters down to a smaller number set of fundamental parameters. A related but independent question is, where do neutrinos get their masses from? Whether it is a Higgs mechanism or something else. All right. All right. So it turns out the simplest way to give neutrino mass is through the so-called scissor mechanism, as Pierre has taught us some 40 years ago. And in scissor mechanism, of course, it requires the existence of the right-handed neutrinos. Given that the right-handed neutrinos, they are not charged under the standard model symmetry, we could just give it the mass without interacting with the Higgs. All right, so that's what this MR is denoting. And now once I have the right-handed neutrino, again, just like the rest of the, just like the charge fermions, now the neutrinos can participate in the Yukawa interaction, right? So those are indicated by the M sub D due to the Yukawa interaction. So of course, this is the simplest version of the scissor mechanism. And I know like several of the participants at the workshop may have your variation, your favorite version of the scissor mechanism. And I can spend the whole colloquium on that. But the bottom line here is that even in the simplest mechanism, scissor mechanism, just by adding the right-handed neutrinos, it turns out that there is a nice way to suppress the neutrino mass. Specifically, if the scale for MR, this right-handed neutrino mass, is very heavy, then a active neutrino mass which are compatible with the observations can be generated. All right, so here just putting some number. If I assume this mass term, which get generated via the Yukawa interaction, just like the charge fermions, assume a value which is like the top mass. All right, and if I take this active light neutrino mass on the order of square root of delta m atmospheric square, it turns out that this heavy scale that is required is very close to the grand unification scale, 10 to the 15 GeV. Right. So of course, the goal of unification, this is the ultimate goal of particle physics. And the hope is that, in a grand unified series, it may offer us a more elegant way in terms of the organization principle. Maxwell, in this regard, Maxwell actually took a very big step by realizing that the electric and magnetic forces are just two different aspects of the electromagnetism. Einstein laid down the way for us to unify gravity and electromagnetism. So we've come a long way since then. So right now, both theoretically and experimentally, we have a very good understanding that the quantum electrodynamics and the weak force at high energies are just two different aspects of one single force described by the electroweak theory. And theorists also know how to unify the electroweak theory together with strong force into the so-called grand unified theory. All right. So of course, to further unify these three fundamental forces together with gravity, we would require perhaps string theory, or if John allows me, something else in order to achieve this unification. But even though we haven't had a real candidates that successfully unify all these four fundamental forces, one lesson learned is that supersymmetry will play a very essential role. And this is indicated. Let me try again. Just bear with me so that you don't get distracted. In this very nice result here, where if I take the standard model particle contents with supersymmetry, what you observe is that the 3 gauge coupling constants of the standard model actually meet really nicely at the scale roughly around 10 to the 16 GeV. And you remember a few slides ago, we just saw that in order to have suppressed enough neutrino masses, the scale for the right-handed neutrino, the heavy scale, is also very close to the 10 to the 15 to 16 GeV. All right, so to address, the mass scale part of the challenge. For the remainder of the talk, I'm going to concentrate on the mixing structure, meaning the interfamily structure. Of course, there are many approaches that exist, but what I will concentrate on is the approach that utilize the symmetries. So in the general framework, generally there are 2 types of symmetries at our disposal. One is a Gauss symmetry in grand unified series, which leads to relations between quarks and leptons. So these are interfamily relations, which of course allows us to have the reduction in the number of parameters. Another type of symmetry is called the family symmetry, which acts as sort of horizontally across the 3 families. So this type of symmetries give rise to interfamily relations, right, which allows us to distinguish the 3 families. So the basic idea is that given the existence of the symmetry, there exists relations among parameters and therefore allowed us to reduce the number of fundamental parameters in our model. And experimentally, the existence of the symmetry is also important because such symmetry may lead to correlations among physical observables, which allows us to test the model or distinguish the model experimentally. So there have been a lot of activities recently building models based on discrete family symmetries. And here I just provide an incomplete list of the discrete symmetries that have been utilized in these endeavors. And of course, this incomplete list, many of the symmetries have simple geometrical interpretations. And of course, a very good source of learning about the group theory of discrete symmetry is Pierce's recent book, which I learned a lot from it. So all these activities are actually motivated by something called the Tribymaximal neutrino mixing. So what it means is a neutrino mixing matrix of this form, all right? So what this entails is that the new 3 mass eigenstates has 0 nu e, an equal amount of nu mu and nu tau. The new 2 mass eigenstates has equal amount of nu e, nu mu, and nu tau, where the new 1 mass eigenstates has 2/3 of nu e, 1/6 of nu mu, and 1/6 of nu tau. That's what that is telling us. And if you have taught, classical mechanics, or you just not so far away from your grad school days, you may recognize that this solution, this eigenvectors I show here, actually are exactly the solutions for the system of coupled pendula, right? So here's a system of 3, uncoupled pendula, identical pendula. If they are not coupled, then the displacement of each of their, then each of their displacement is a normal mode. Meaning, if I start the oscillation of one, it will just continue forever, right? And they are not connected. However, if I, now introduce 2 identical springs that connects these 2 pairs of pendula, then the individual displacement is no longer the normal mode. And you can just go ahead, write down the Hamiltonian and solve the system and find the normal modes. And what you find are the following solutions, which coincide with the solution in the TBM mixing patterns. And I will fix it again. Yeah. Right, so these are the solutions of precisely those eigenvectors that form the tribimaximal mixing matrix. So this is actually kind of neat. All right, so if I take the TBM mixing patterns, what you find is it predicts at atmospheric mixing angle, which is exactly maximum. It predicts a solar mixing angle. When I write it in terms of sine square theta solar, this gives the value of 1/3, right? And if you take these values, compare them with the specific values from the experiments, they actually are agree quite well, right? However, if you look at the prediction of theta 1/3, this is exactly 0, right? So, after the theta 1/3 discovery, this basically kills, not use that word, it basically ruled out the TBM mixing pattern. Okay, so the general approach is to say, well, the TBM mixing pattern, which, as I will show you, can arise from underlying symmetry. This is a leading order prediction of the model. And of course, exists possibly calculable or sometimes incalculable corrections that may bring the model predictions to be in agreement with the experiment. All right. So as I advertised, the TBM mixing pattern can arise from an underlying A4 symmetry. So A4 symmetry, this is a symmetry of a tetrahedron. It describes even permutations of 4 objects. So it has 12 elements. The group is generated by 2 generators, T and S. So T is even permutations of 1, 2, 3, 4 into 2, 3, 1, 4. Geometrically, this corresponds to the discrete 120 degrees rotation, discrete rotations about this axis that leave this tetrahedron invariant. Right? Where the second generator S, this is a permutation of 1, 2, 3, 4 into 4, 3, 2, 1. And geometrically, this corresponds to the discrete 180 degrees rotation about this axis, which leave this tetrahedron invariant. This group and the representations are defined through this algebra, where if I take S squared, ST cube, and T cube, this give me identity, right? So this is a group. All right. So if I impose this A4 flavor symmetry on my Lagrangian, A4 is spontaneously broken by the so-called Flavin fields, which can be thought of as a Higgs field, which break the flavor symmetry. All right. So upon the spontaneous breaking of the A4 symmetry, this is a resulting neutrino mass matrix. So of course, I'm skipping a lot of details here. This is actually generated by 2 Flavin fields. But the bottom line that I want to draw your attention to is this resulting effective neutrino mass matrix only contains 2 free parameters, C0 and this parameter U, right? And what you see, these numbers of 2, -1, +1, this which describe the relative strength of this mass matrix, elements in the mass matrix, this correspond to the Clebsch-Gordan coefficients of A4. And what's interesting about this mass matrix, and I think that was the reason why it generated so much attention, a few years ago, was the fact that no matter what values C0 and U assume, this mass matrix is always diagonalized by the TBM mixing matrix, right? So, in other words, the mixing angle predictions in this setup is totally independent of the model parameters. It's all fixed by the A4 group theory. Right. So what do this all have to do with the modular flavor symmetries? Right. So torus, these are donuts. A torus, it can be constructed from the parallelogram, basically by identifying the two opposite edges and glue them together. Right. In other words, I can cut off this torus along its two cycles and recover the parallelogram that I started out with. These two edges in the parallelogram, this actually corresponds to the lattice basis vectors. And points in the planes that are differed by lattice translations are identified. So there's the periodicity there. As we see, the choice of the lattice vectors are not unique. And equivalent tori are related by the modular symmetries. So to be more precise, this transformation from one set of the lattice vector to another set, these are related by this modular transformation described by this 2x2 matrix, where the elements A, B, C, and D are all integer, and this matrix has determinant 1, so that the volume of the fundamental domains stay the same. Okay. Right, so this corresponds to two basic transformations for the yes. One is the lattice translation, which is described by the generator T. Another is corresponding to the swapping of the lattice vectors, which is generated by S. In terms of the complex coordinates, meaning the modulus parameter, which is defined as a ratio of those two basis vector E2 to E1, this two transformation can be seen as follows, whereas would take this modulus parameter, map it to 1 over tau, where the T transformation would shift tau by 1 unit. Okay, and SNT generates the SL2Z and satisfy this condition, namely S squared equals to ST cubed equals to identity. All right. So the finite modular groups, they can be obtained as a quotient group of the modular symmetry. I'm not going to go through this detail, but just show it there so that you can read by yourself. But the key point here is that the generators of the quotient groups must satisfy this additional condition, Tn equals to identity. All right. So with different numbers of n, we actually recover, we actually obtain some of the non-abelian discrete groups that we encountered earlier as the finite modular group, the quotient group of the modular symmetry. All right, so what does this have to do with neutrinos, right? If I take my Lagrangian, a general Lagrangian would have the following structure. You will have some coupling constants, Yukawa coupling, for example, multiplying by the operator formed by the fields, right? If I impose the modular symmetry on the Lagrangian, my modulus parameter has to go through this modular transformation, where all the fields would transform as some representation of the finite modular group. Okay. In addition, they also transform with this so-called automorphic factor. Okay. So if I demand modular symmetry on my Lagrangian, you can actually not so hard to see that my Yukawa couplings must transform as the modular forms, which is defined right here. Okay, so the modular, so-called modular weight k here is uniquely determined depending on the modular weight from the fields, because all the the phases all have to cancel, right? Basically. Furthermore, the representations have to, the products of these representations have to generate an invariance in the end, so that I ensure the Lagrangian is invariant under the modular symmetry. All right, so as an example, let's just take this Weber operator just to see how it works. So now I concentrate on the Weber operator. Here is my Yukawa coupling. In the setup with traditional A4 flavor symmetry, the Yukawa coupling is replaced by the flavon vacuum expectation value. And in this setup, the flavon has to transform as an A4 triplet so that it can form an invariant. So for general A4 triplets, it will contain 6 real parameters, right? And therefore, the resulting neutrino mass matrix will be of this form that contains 6 real parameters. A, B, and C are all complex. In contrast, if my setup has modular A4 flavor symmetry, right, then the Yukawa coupling is replaced by the modular form. And again, the modular form has to transform in this setup as an A4 triplet, right, and satisfy various conditions from the modular symmetry. And so what that means is Y1, Y2, Y3, they will have relations among them, but all of them are controlled just by 2 real parameters, namely the modulus parameter tau. Right. So in that case, the resulting neutrino mass matrix, which is blocked right now, let me try to fix it. Would have this form, right? So everything is just controlled by the modulus parameter tau. So these modular forms, in some situations, have not been calculated, but in some cases, they can be calculated explicitly and are known. And without boring you with the detail, but just to show explicitly, this is the Y1, Y2, Y3 functions that we saw on the previous slides, and everything is just controlled by that tau parameter. So how good is this? In this very simple Toy model with just the Weber operator, it turns out that the entire neutrino mass matrix doesn't have any free parameter rather than the modulus parameter tau. With a choice of tau having this value, which is very close to the subdual points, this is a set of predictions, which I put in the purple box, right? So, as you can see, except for theta 1,3, which is a bit too small, all the rest of the predictions agree with the experiment quite well. Of course, we haven't measured CP yet, but what you can discover is that the predicted CP value of the Dirac phase is also quite nice, right? And if you further fix the values of the Higgs-Webb square to the cutoff scale, just one number, you can also predict all the 3 absolute masses of the neutrinos, which of course would agree with the observed 2 delta m squared. So this is actually rather robust, right? And of course, with some tweak of the models, one can further bring this toy model to be closer and to be in agreement with the model, with the experimental data. All right. So of course, this contribution, this result, what I show here, these are based on the holomorphic contributions, and these comments are more for the experts. So for the expert in the audience, you may worry about the fact that generally the non-holomorphic contributions may lead to large corrections to the predictions. But what we found in this very recent paper, together with our students Victor, Mario, and Shreya, and my senior colleague Michael, who is also here, as well as Saul, we found that actually corrections to the kinetic terms in this kind of setup can be under control. All right. And modular flavor symmetries can also have possible UV origin, as Andrea Chalmers, who is in the audience, has studied in great details with his collaborator. Modular flavor symmetries may also come from string theories. And more recently, together with our students, Yahia, again, Victor, Saul, Michael, and Shreya, we found that modular symmetries can also from magnetized tori. All right, so before I end, I just want to acknowledge a very diverse group of very talented collaborators I'm very fortunate to have. From whom, all right, from whom I learned a lot, both on the series of neutrino masses, as well as the phenomenological aspects of neutrino physics, which I didn't have time to talk about. So this includes our current and incoming graduate students at UC Irvine, and also grad students at UNAM in Mexico, as well as two former grad students at TU München in Germany, including Andreas here, who is right now a postdoc at Max Planck Heidelberg. And also my two former UCI undergrad students are now in grad school, as well as two undergrads that I'm currently working with. I would also like to thank my senior collaborators, especially Michael, who is here, and Saul, who have taught me a lot, the UV aspects of the modular symmetries. And also thanks to Michael for helping me with making the animations. All right, so to sum up, the fundamental origin of fermion mass and mixing patterns is still unknown. Neutrino masses have provided the very first compelling, solid evidence for physics beyond the standard model. In this talk, I've concentrated on the approach of symmetries, which provide an understanding for the pattern of fermion masses. And the keywords here is really correlations, right? This includes the correlations among the model parameters that are afforded by the symmetries, as well as the correlations among the physical observables that may be tested experimentally. The non-abelian discrete symmetries are essential and actually very interesting because this is a framework where the mixing patterns can come from the group theory, the Kapsch-Golden coefficients. In particular, there's a very interesting, exciting new possibility where, due to the complex Kapsch-Golden coefficients in certain discrete group, this offer a novel origin for CP violation. Okay. If we promote the non-abelian discrete symmetry to be the finite modular flavor symmetries, this leads to increased predictivity. In particular, in the extreme case, the entire mass matrix can be controlled just by the shape of the donuts, the torus, right? And in this framework, the corrections to the kinetic terms can also be made under control. And lastly, there could be possible UV origin of this modular flavor symmetries. Right? So, at a broader scale, right now, experimentally, we still don't know what is that operator, what is the underlying physics that generate the neutrino masses. I just show you one possibility, utilizing physics at a very high scale, close to the grain unification scale, that could give rise to very nice result for neutrino masses and mixing. But of course, given that we don't know what the operator is, what the scale is, the possibility actually is very open. The scale can range from Gus scale all the way down to the TeV scale. So, for the TeV scale or low scale type models, there could be additional direct probe from the LHC or from other low energy experiments, as many of our participants are working on and experts on. On the cosmology side, neutrino physics may also have conceivable relevance for the generation of baryon number asymmetry through the so-called leptogenesis mechanism. In addition, it is the standard belief that there's a cosmic neutrino background, which can take us back to the very first second. And of course, we should also be open for the unexpected, such as the non-thermal radiant neutrino, the existence of the non-thermal radiant neutrinos, which may offer another window into very, very high energy physics. All right, so just a little advertisement. There will be a workshop at Bonn next year and on modular flavor symmetries. And our organizer, Michael, is right here. So it is May next year, which hopefully we can really go there and meet in person. And I know several of the participants will be there as well. And just to thank you for your attention.
Thank you very much. Thank you very much, Mu-Chun, for the wonderful talk. So I think we can open the floor for some questions. Please use the raise hand button or raise hand function, either in person or remote in the room. I try to monitor the questions. Any questions to Mu-Chun? Yes, Gordon, please.
You seem to have predicted inverted hierarchy. You look at mass at the bottom.
Yeah.
You need to repeat.
All right, so the question is, in the slides where I show the prediction of the modular symmetry, and Gordon actually very observant, found that it's inverted hierarchy. And the question is whether all the setup based on modular symmetry predict inverted hierarchy. And the answer is no. This is very specific to this TOEI model. So with additional tweak, in particular, there's a follow-up paper by Ferruccio and his collaborator, where they adding one additional parameter, and that can bring all the predictions to be in agreement with the data. And I believe in that case, it's not necessarily the inverted hierarchy.
Any further questions? Hakari, please.
It's not a comment, not a question, because you kind of made emphasis on the prediction of several models that neutrino masses are zero. Okay, it's maybe partly terminological, but I would say that it's not a prediction, it's the assumption of standard model, because you said that there is no right-handed neutrino, and that's why zero. But to include right-handed neutrino in standard model, there is no problem, right? So there's a symmetry group of standard model is the heart of standard model. It doesn't depend on this assumption. So no, it's okay, but it's not a major issue. But it's not just you. It's often you can listen that it's like some deviation of standard model. I would not call it some deviation by itself.
All right, so let me repeat the comments so that the audience in the Zoom can hear it. So the comment from Arkady is that I made these statements that standard model predict massless neutrinos because there are no right-handed neutrinos. But this is not a prediction, so the neutrino of the standard model, but rather it's my assumption where I define my standard model without the right-handed neutrinos. Is that correct?
Yeah.
Right, so of course, if you define your standard model with right-handed neutrinos, that's fine. But I think there's another distinction, meaning if I could embed, the whole framework into Scissor Mechanism based on, say, SO10 grain unification, there the right-handed neutrino is predicted, right? First of all, secondly, there is also a reason, a physics symmetry reason, why the right-handed neutrino mass has to be heavy. Yes. Which this reason doesn't exist if I just have a standard model including the right-handed neutrinos. Do we agree?
But no, but like different type of neutrino. Scissor mechanism is a separate issue. And existence of just partner, right-handed partner, related to right-handed partners from neutrino and direct mass, then it's not excluded.
Sure, yeah. Right, but then you have to live with this very, very tiny Yukawa couplings. Right. So yes, we are in agreement.
Since you have this slide up, just out of curiosity, if you take this toy model and you vary the tau parameter in the complex plane over some reasonable range, how much do all these numbers do?
All right, so very good. So the question is, here I only show you one particular number for tau, which has this prediction, which is not exactly, there's something off for theta 1, 3. And Andre's question is, if I vary parameter tau, how much improvement can I get? Yes? Or
what kind of range is the parameter space use?
so, okay, very good. So what kind of parameter space in terms of the predictions, right, that the model has? So in fact, this value of tau is a best value for the experiment. I don't know the range for full range for all the predictions. But the bottom line is, this is a best fit of the model.
So let me try to ask the question again. So what's impressive about this proposal is that you only have 1, 2 parameter.
Or 2 free parameters.
Other than the overall scale to get all the mixing parameters. And the fact that you can come close to the experimental data is sort of impressive.
That's right.
However, if you tell me that by varying tau over lots and lots of different numbers, you can span the entire set of possibilities for all of the mixing numbers, this is a lot less impressive. So the question is, how close are you just by saying that you have this modular symmetry and then the tau just adjusting so that you can fall into the right place? Or does the tau allow you a lot of freedom to move around in the parameter space?
Right. So the question is, so I rephrase that. It's okay. If I vary the tau parameters and if I can generate all the values for the mixing angles, then this prediction, I mean, the scheme is not really that impressive at all. My understanding is by looking at the specific models based on, of course, more complicated than this, some models, like some groups, they do look at the entire parameter space. And my understanding is it's not everywhere. There are restricted regions for the predicted values. Of course, what the restricted region is, that would depend on the specific construction of the model.
Are there any questions from the audience on Zoom? Oh, yes, I see one. Joy Rosner, could you please unmute yourself and speak up?
Actually, Joy is my wife. I'm using her account. This is John Rosner.
Hi, John.
Hi. My question is, the tribimaximal mixing looks like a limit in which some perturbation is set equal to 0. And I wonder if you have models where that perturbation is related to the to the quark mixing matrix. In other words, the 0th order is tribimaximal, and the 1st order is one where tribimaximal is perturbed by something which is related to the quark mixing. So you have a reduction of parameters. Probably also you have the relation, the SO10 relation between the tau mass and the top quark mass.
Yes, so thank you for the question. That's some aspect that I didn't cover. But yeah, so beyond just going back to, I think, Joe, your question refers to the just traditional flavor symmetry setup. And indeed, Katie and I, we actually had a model which is based on SU5 together with a double covering of A4, the so-called T prime group, because that's what's necessary in order to get double representation so that we can accommodate the quark sector. And there, of course, I mean, do I have a shot somewhere? Right, so the PMNS matrix, of course, is the, I may not do this right, but anyway. The products of the neutrino diagonalization matrix together with the charge lepton diagonalization matrix. And for the neutrino part, even though this is exactly TBM, which predicts 0 theta 1, 3, we could get correction coming from the charged lepton sector, right? And given that this is a grand unified theory setup, there is a correlation between the lepton mixing angle and the quark mixing angle. And that's actually a very nice prediction, which of course, unfortunately, is ruled out. 3 times root 2, I think this is right. So the prediction we have is theta 1, 3 is roughly theta Cabibbo divided by 3 times square root 2, where the 3 and square root 2, these are the Collapse-Golden coefficients of the gut group, SU5, and the T prime group, right? And of course, this value is way too small, but on the other hand, it is so robust that you can rule it out with experiment. So that's one example that I'm familiar with, and there are indeed other examples, either with the corrections from the charged lepton sectors, or there could exist the non-holomorphic corrections, such as in the supersymmetric setup, you could have corrections from the Kähler, Kähler potential due to the non-canonical kinetic terms. Right, so there are various ways where the correction can bring the prediction of the model to be consistent with experiment. So I hope that answers your questions, John.
Yes, thank you.
In the interest of time, please join me again. Thank Mu-Chun very much for the wonderful talk. So everybody, yeah, have a great evening.